Thank you very much. So I was just waiting there because our online guests were watching a short video playing through. So thank you very much for your patience. And good evening, very, very warm welcome to this year's annual Wade Lecture, which I'm delighted to say we're holding as a hybrid event tonight. So we have guests online, guests here in person, welcome, and over 300 guests joining us from around the world online. So warm welcome to you all, staff, students, alumni and supporters who've joined us for this evening's event. The Wade Lecture was established in 1970 following a gift from the Wade Foundation, which was set up by Mr. E.J. Wade of Dimplex. So there's an engineering connection there. I am Professor Diana Eccles, Dean of the Faculty of Medicine and Professor of Cancer Genetics. Just a bit of housekeeping first. Before we begin, for those in the room, there are no fire drills planned. So if the alarm goes, we will need to evacuate and go to the muster point, which is by the interchange where the buses come. Once we've heard from our speaker this evening, my colleague, Professor Roxi Carare, head of the School of Clinical and Experimental Sciences, with research interests in dementia and neurodegenerative diseases, will be hosting the audience Q&A session. Please do start to think about any questions you have. We've already had a few online. For those of you joining online, you can also submit questions using the Q&A box, which you can find on your screen. And for those in the room, we will ensure that you have a microphone so that everyone can hear the questions both in the room and online. The Faculty of Medicine has a research strategy that aims to leverage interdisciplinary approaches to discovery, data, devices and delivery in order to engineer better health. We have research links across all 5 faculties, as well as a global focus on key challenges in health. We are hugely fortunate to work in close partnership with one of the biggest and best teaching hospitals in the UK, University Hospital Southampton. Their support of our research is testament to their understanding that high-quality research is required to deliver world-class patient care. Dementia is our spotlight this evening. And a recent BBC story, which was circulating on the slides at the beginning, covered our recent grant success for a dementia clinician at the hospital in Southampton and our biophotonics expert, Sumit Mahajan, whose funding will help them develop a new laser-based, super-accurate diagnostic blood test that could transform the early diagnosis and treatment landscape for dementia. Now, on to tonight's speaker. I'm delighted to welcome Professor Joanna Wardlaw to Southampton. Joanna is Professor of Applied Neuroimaging at the University of Edinburgh, Foundation Chair in the UK Dementia Research Institute and Consultant Neuroradiologist for NHS Lothian. Her work focuses on understanding the brain and its blood supply and on treatments to improve blood flow to the brain, including thrombolytic drugs that are now in routine use to treat stroke and more recently on treatments for small vessel disease and vascular dementia. This evening's lecture will highlight important milestones in the development of modern neuroimaging and discuss key insights that are driving advances in common brain diseases. These include primary diseases of the blood vessels, such as stroke, and diseases of the neurons and supporting glia, such as dementia and multiple sclerosis. So, Joanna, without more ado, I would invite you to give us the annual Wade Lecture.
Well, Professor Eccles, colleagues, thank you very much for the kind invitation. I hope you can hear me okay. First thing. So it's a great privilege to give this lecture. I'm a neuroradiologist and I've been using brain imaging to research the brain for a long time, and I hope to give you a few examples of the sort of things, sort of insights that has been possible to develop, and also a little bit about the background of neuroimaging, some new treatments that are emerging and where we may be going in the not too distant future. And I know this is a big interest in Southampton as well, so hopefully this will be relevant. I have a number of academic grants, but no industry funding or other conflicts of interest. So I'm going to say a little bit, just a tiny bit, about how we got here from the history of medical imaging. It's all happened very quickly, and I think sometimes it's very easy to think that we've had these amazing scanners for years, but it's a bit more recent than you might think. A few key things about the brain, a bit about how my research I think of it as using medical imaging as a kind of modern microscope, and how it's absolutely fundamental that this is only possible if you have a really good interdisciplinary base of physics, engineering, chemistry, biology and medicine. It simply isn't possible otherwise, and where we may be going in the future. So just starting with a very brief history of medical imaging. So X-rays, on which all of this is ultimately based, were discovered 129 years ago by a German physicist who wasn't trying to discover them, he was just messing around. And I have a few important points to make in the context of this lecture, one of which is that sometimes you find something when you're not expecting to find it, and you should be very open to new ideas and so on. And he was messing around with cathode ray tubes, and he noticed that there were funny shadows emerging. And he obviously thought that this was all a bit weird, and he did some little experiments and saw shadows of himself. And then 2 weeks after that, by that time he'd messed around with it so much that he decided to take a picture of his wife's hand. And this is the first ever X-ray, if you like. It's a very famous image. Now that was in November 1895. And about 8 weeks later, not only had this been published in the journal Nature, but it had been accompanied by at least one other person in the UK being able to generate an X-ray of their hand. That's how fast this happened. They didn't have TikTok. They didn't have, any of the X or whatever. They didn't have the internet. They barely had telephones. And the motor car, as a modern convenience, had only been invented about 10 years previously. So, human communication is phenomenal when it really wants to be. And it just astounds me how quickly all that happened. And very quickly, formal X-ray departments established themselves all over the country. And this is the front cover of what was the first ever day book to keep a record of all the X-rays in the Edinburgh Royal Infirmary, which was introduced in 1898. And very amusingly, I thought, I hope you can see this, the first ever page on this X-ray day book. It was started on October the 14th, 1898. And the request was because of a pellet in the eye. And you'll be interested to note that the result of the X-ray was a failure to find the pellet. And that's another theme, because we do an awful lot of medical imaging examinations and we don't always find what we're looking for. So that's how it started, and it's still going on like that. But nothing comes without a price. And it's easy to look back and forget about it all, but in the early days, they didn't know how dangerous X-rays were. But over a period of years, and it took a period of years, it became apparent that the people who were working most closely with the X-rays were developing problems with their skin, their fingers, all sorts of other radiation-induced conditions. And by 1936, they had actually erected a monument to what's referred to as the radiation martyrs, many of whom came from the UK. And by 1959, there were 359 names. Now, that monument was put up only about 40 years after the X-rays were first brought into use. We're only now at that 40-year mark for the introduction of MRI. And of course, magnetic resonance imaging. And of course, we're, I think, more careful than we were in those days, and we haven't yet found a really horrendous, unexpected side effect from magnetic resonance imaging. But don't hold your breath. It could be, around the corner. And I think it's worth bearing in mind just how much has gone into the development of this field, and people being prepared to try things out and perhaps we should be more careful. So the next big step forward was the invention of CT scanning, or CAT scanning as it's referred to, and this was due to the imagination and insight of someone who was an engineer. He'd been in the RAF, no medical training whatsoever. He worked for what was then called EMI, a famous British company that no longer exists. He'd done a lot of work on things like signals, radar, processing. He was involved in early development of a transistor computer, which helped to make things much smaller and more doable. And in the early 1960s, he got this idea that you could somehow find out what was inside an object by shining a series of X-rays around it, picking up the X-rays as they came through, and then using a computer to back project and integrate what those X-rays must have gone through. And he tested the first prototype on a preserved human brain, and then a cow's head, and then himself. And that's another theme in this lecture, because many of these things people have had to try on themselves and demonstrate that they work before anybody paid any attention. And again, things happened really, really quickly. So in 1971, that was the first ever CT scanner. It was in a hospital in London, and there was very rapid uptake. And we got one in Edinburgh in the late 1970s. And somebody said, "What do you want that for?" And fortunately, my senior neuroradiology colleague, who, this is way before I did neuroradiology, said, "Oh, we'll have one of those, thank you very much. We don't care how much it costs." Because they could see just how valuable it would be. And of course, that was one of a number of Nobel Prizes which have been handed out for medical imaging. So this was a 1976 brain scan of somebody with big ventricles, too much water stuck inside their head. And just to get that very, very basic few slices took an hour. And of course, things have very rapidly advanced, and you can now get an entire brain with all of the blood vessels and the tissue level blood flow in about 7 minutes, including sticking in the needle to give a contrast injection and so on. And now with artificial intelligence, you can get some of that information coming to your mobile phone, and everything is faster, and trying to reduce radiation doses and so forth. So really rapid changes. The next big advance that I just want to mention is about magnetic resonance imaging, because this is also very, very recent. And this image here of these two scratchy blobs is the first ever MR scan of two chest tubes of heavy water in a bucket of ordinary water. And this was an early prototype human MRI scanner built at the University of Aberdeen. And the very first scanners were introduced in the early 1980s. They were all very low field. We didn't have high powerful magnets. They were also put miles away from main hospital buildings because of the potential danger of the magnetic field. But anyway, they've advanced very, very rapidly and have gone on from detecting structural changes to using it as a sort of sensor for chemicals in tissues, to understand more about what's going on in terms of function in your brain. This is an example of a functional scan where you can see the bits of the brain that are lighting up in response to movements. And you can actually use this now to work out what somebody is thinking, including somebody who is actually unconscious. So really, really powerful techniques. You can look at fiber structures and so on. And so this just summarizes really where we've got to. We now have, over the last 100 and so years, a whole range of different techniques, including ultrasound. They all are based on using waves or particles or both to do something. And imaging all sorts of different organs and telling us all sorts of things about what's going on inside and diagnosing disease and so forth. Really, really, really powerful techniques. So I then just want to say very briefly a little bit about the brain, a few key facts. Because the brain itself, I think, is a quite remarkable engineering miracle. And those of you who are engineers might like to just think about this briefly. So the brain is uses a lot of power, about 20 watts at rest, which is a bit like a dimly glowing light bulb. So you are like a group of rather dimly glowing 20-watt light bulbs. It doesn't have anywhere to store its energy. It relies on a constant supply of sugar and oxygen. It takes about 20% of the whole cardiac output, the blood flow that's going around your body, at rest, and whenever you start to do something, you need more blood to supply that, sugar and oxygen. And it's also got to get rid of a lot of waste and heat. You know, think about how hot your laptop gets. You know, your brain will generate heat as well. It sits inside a very hard case because it needs to be protected, and it's like taking your laptop and sticking it in a bucket of water because it's immersed in spinal fluid, it's got blood going through it. It's basically a computer sitting in a bucket of water, and I don't think we've yet quite solved that one in terms of other physical computation. In order to get all of that energy, it needs a very, very effective blood supply, and it has a huge mesh of tiny blood vessels, about 650 kilometres, which is roughly the distance between Edinburgh and Southampton, if not a bit further, so that it's got a very effective blood supply. The surface area, because the exchange of oxygen and glucose has to happen over a large area, is about the size of a tennis court, all crammed inside your brain. And about, a fifth of the cardiac output is roughly 1 to 1.5 litres of blood going through your brain every minute, which is equivalent to 3 cans of lager. Other brands are available. So, it's a phenomenal piece of engineering, and it's not surprising that when something starts to go wrong, and it's very surprising that more things don't go wrong. So just hold those thoughts. I would now like to give you a few examples of how I have, and with colleagues, been able to use these medical imaging technologies to try and get information about what is the pathology, what's going wrong in the brain, and work out, what we can do about blood vessels diseases, particularly in relation to stroke and dementia. So this is just to orientate you partly, but these two images are two different sorts of magnetic resonance scans, and they show the brain in different ways. They're obtained as part of the same investigation, but you can use them to show different features in the brain depending on what you want to highlight. And in your youth, you have a brain that fits quite snugly inside your skull, and you have these structures here, which are the fluid-containing ventricles, and then there's fluid over the surface of the brain to give it protection and buoyancy. But as you get older, to varying degrees, the brain tends to shrink, and so something has to take up the space that's left in that box, and so you get that's replaced by having more fluid and larger ventricles. And you also develop typically some of these sort of tissue areas where you can see these what are called white matter hyperintensities. And these two are common accompaniments of aging, but they happen to a very, very variable degree. And they have so far been, in general, written off as if they are normal accompaniments of aging. But when you've got variation like that, it can't possibly be normal. And in fact, we now know very well that typically brain volume loss is more associated with memory changes and development of these abnormalities, primarily in the white matter, affects things like executive function and processing speed. And the more you have of these, the more you will be likely to have some degree of cognitive decline. The more of these you have, the higher your future risk of stroke, and also the higher your future risk or current risk of dementia. So what particularly got me involved in this, because I've been doing a lot of studies of the brain as it gets older, trying to work out why is it that some people seem to lose brain and lose brain function faster than others, and what's going on in the blood vessels particularly. And a number of years ago, just sitting in a routine X-ray session, I saw the scans of a gentleman who was in his 70s, and he came in with a very particular sort of stroke symptom, which is very common. It's about a fifth of all ischemic strokes, and he had this MR scan. And what was interesting was that in the middle of his little stroke was this funny little linear thing here, which looked just like a blood vessel with a bit of a blood clot in it. And that hadn't been described before, and it's something that you sometimes see in bigger blood vessels, but not in these little tiny blood vessels deep in the brain. And I sort of thought, well, what on earth is it? Is this just a small version of a bigger clot, or, what's going on? Is it something else? And how does that fit in with these other white lesions that tend to develop and that we see commonly? Because these are very common in this particular type of stroke, lacunar stroke. They've been assumed to be areas of lack of blood flow or to be ischemic. And they've all been attributed to high blood pressure and other vascular risk factors. But is that necessarily the case? And I think, with apologies to our rail transport system, observation. If you see something that doesn't quite make sense, it's worth digging into it a bit more and trying to work out exactly what's going on. And so, cutting a long story short here, this small vessel disease, this disease of the little blood vessels deep in your brain, which causes the symptoms such as lacunar stroke, also turns out to be a major cause of large hemorrhages, which occur in older people particularly. I've mentioned these white matter hyperintensities. There are other features like these little holes in the brain, or these little microbleeds, or perivascular spaces. And then you get things which you can't see unless you use fancy techniques like something called diffusion imaging, which allows you to track the white matter fibers. And so here you can see all these little squiggly lines are the white matter fibers with these little white matter hyperintensity dots in here affecting the white matter tracts. And so basically the visible disease on a conventional scan is just the tip of the iceberg. The more of these you have, the more that they lead to remote secondary damage and secondary brain volume loss. It's responsible for about a quarter of all strokes and somewhere between 20 and 45% of dementias. And unfortunately, at the moment, there is no effective treatment, either for the stroke aspect of it or for the dementia aspect. Yes, of course, you have to try and manage people's blood pressure, but beyond that, there's really nothing specific. And it turns out that actually, this is nothing to do with little clots or blood clots in the vessels or emboli or whatever, but what we call an intrinsic pathology in the small vessels. This is a sort of mild, and this is a more severe case. And because it's nothing to do with clots or emboli, it's really no surprise that the conventional ways in which we would normally try and prevent another stroke from happening don't work very well in this group. So a few things that we've seen on imaging, which we would not have been able to see had we not been using the imaging, include the following. So first of all, when people see a brain scan, for some reason, they assume that that's what that person's brain always looks like. Now, if you saw a photograph of somebody leaping into the waves, you would realize that if you'd taken it a second earlier, you would have seen them in a different position in the leap or whatever. And actually, the brain is no different. It's not a static object, but nonetheless, that's kind of how people think. And I just want to show you a few examples. So this is a study in which we recruited a group of patients, and we deliberately put them in the scanner at about 2 monthly intervals over a period of a year, regardless of whether they had any of these symptoms or not. And what we saw was really scary. In a large proportion of people, every time we put them in the scanner, you would see another of these little tiny white dots, like on the top row here. And these are little areas where they've developed another one of these little lacunar stroke-like lesions, except that in the vast majority of cases, they didn't have any symptoms. So if we hadn't put them in the scanner, we wouldn't have known this. And this just illustrates the distribution of the little minor tiny strokes that they had when they came into the study. And these are the ones that developed over the course of a year. These were all people who were on full, usual prevention treatment to stop them having another stroke. And in this particular instance, it wasn't actually stopping it, which just makes the point that this is not like other types of ischemic stroke. And the only things that we've been able to find that this is related to are having worse of these little vascular lesions to start with. And in fact, it turns out they are actually associated with really subtle symptoms, but you've got to look for those symptoms or you won't find them. Why is it that some of these little lesions cause symptoms and make people go to hospital and complain about having had a stroke, and other ones can gradually accumulate in your brain without you knowing it? And it's very simple. Again, the brain is a piece of mechanics. The ones that cause symptoms tend to land in your primary motor and sensory pathways. So if you get a little lesion in a pathway that controls your hand or controls, a particular motor or sensory function, you're much more likely to notice it than if it lands in one of these other, shall we say, more executive areas where a small lesion is not going to suddenly stop you moving your hand or doing something obvious of that nature. So I think there's a simple basic mechanics. Just because you didn't know you had it doesn't mean it's not happening. And these abnormalities have a very variable evolution. So that's the other thing. If you do a scan much later, you may or may not see the presence of one of these little lesions, even if somebody's had a very clear stroke. So for example, in this case here, this is the original presentation, 3 different examples, but that one at the top there with that big white blob is this one here a year later. It has completely disappeared. And so some of them disappear transiently and then they reappear. Some of them form a little hole. They've actually punched a hole in the tissue. Some of them disappear completely. You would never know that that person had ever had anything wrong in their brain, apart from the fact that they remember having had their symptoms. And some of them develop little areas where it looks like there's a bit of oozing going on, and that seems to be related to blood-brain barrier changes and so on. Another thing which is clearly much more variable and has a mechanical element to it is these white matter hyperintensities, which I've mentioned. Now, the traditional thinking is that these just gradually get worse, relentlessly. And they're fixed tissue damage, because that's what the pathology has told us. But it's important to remember that pathology is an end stage, and then you're trying to backtrack from what you can see in that brain specimen. But it doesn't tell you how many cycles something might have gone through or whatever. And some years ago, we noticed that there were some people whose white spots got smaller. And they very definitely got smaller. There's no arguing about it. And this was exactly the same scanner, exactly the same methodology. And then we saw other examples. So here, where there was quite a lot of this white stuff, disappeared subsequently. And we found that this happens in maybe 1/5 of people, at least over the first year or two. And we've looked at this across a range of different populations. We've looked at it in people presenting with a small lacunar stroke, or people attending in a study of people with cognitive problems in Toronto, or in a healthy aging study. And if you split people into those in whom the lesions definitely grew, those in whom they shrank, and then there's the people in the middle. So this is sort of what we might call quintiles. It's like 5ths of the population. The ones in the middle have not changed very much, and this is over a period of a year, and that's actually 6 years. You're getting that same pattern. There's a sort of group of shrinkers, and then there's a group of growers. And this has been related to the shrinkers having less recurrent neurological symptoms. And now we've been able to look much more closely and do some objective tests of things like walking speed and manual dexterity. And we've seen that people who shrink don't slow down, and their manual dexterity actually improves. So it's like, the brain is a very mechanical object. And when we look at their cognitive function, and you can look at different aspects of cognitive function, and I'll just take you through this. There's something called general cognition, which is like your general ability to remember things and your general ability to do puzzles and stuff like that. And then there's something called processing speed, which is more about how quickly can you do things and how quickly can you work out things. And what's very interesting is, again, here's the shrinkers, here's the growers, the shrinkers, the growers. For general cognition, you can see that, and this is getting worse and this is getting better, the people whose lesions have grown have clearly got worse general cognition over a period of a year, whereas the people whose lesions shrank have got faster in terms of their processing. And it's almost like somebody's been nibbling at the wires, and then the wires get repaired, and so you can go faster. So what this tells you is that this is not permanent damage. It can't be if it gets better, and if the getting better is associated with real improvements. So having just got to the point where we've recently finished this work, I think it's absolutely astounding what's going on in your brain. You have absolutely no idea about had we not done the imaging. And basically, the white matter where these lesions occur is the wiring. And if you have something which is essentially these hyperintense areas gnawing away. This is a magnified image, gnawing away at these fibers. They're sort of chewing away. It's like having mice in a telephone exchange or something. Then it's not surprising if the telephone connections start to not work quite so well. The other thing that's interesting is that actually in the lesion itself, the tissue damage is the worst. But if you keep taking samples further and further outside the lesion, you can see there's a sort of gradual resumption of normality. So again, it's this thing that it's abnormal in the lesion, but it's also abnormal in the other tissue, and there's a kind of gradient stepping outside. So I just want to say a couple of things about the blood vessel function and what's actually going wrong with the blood vessels. And one of the things that happens is that they leak a bit. And so this is one of the techniques that we've used, which is to measure the if the blood vessels going through the brain are leaking or not. And this is subtle leakage. It's not big leakage, it's subtle leakage. And basically, we give an injection of some magnetic dye through a pump, and then we do some scans immediately afterwards. You can track it going through the brain. And here is one of our physicists trying it out on himself, very much like it has been for centuries. And you can use that information to generate a sort of pizza map of what the leakage looks like across the brain. And here's the corresponding structural image. And you can also do things like contour maps. And what you see from that is that the leakage is worse in the visible lesions. It gets worse if you have more of the visible lesions. And as you move away from the lesions, it gets less. Again, it's happening across the brain, but it's worse actually in the lesions. And then you also get these little areas, if you like, of leakage hotspots. And it's often at the edge of these lesions where they may be growing, as if that's where they're newly forming. And I suppose it's not that surprising if that's what some of the blood vessels look like, then they're probably not working terribly well. And actually, some of this material that you see on the histology is evidence of leakage. And these are areas of active vessel failure. The other thing that goes wrong is that you have problems with the ability of the blood vessels to open and close. So open to increase the blood supply when you're doing something and you need to get more blood to a particular part of the brain. Again, one of our team trying it out on himself. This time you wear a mask and you breathe air, and then you breathe air which has some extra carbon dioxide in it. Carbon dioxide dilates your blood vessels, and you can measure that degree of dilation by doing a scan at the time. And if you just watch this, hopefully it will run. As the person breathes the carbon dioxide, they get more opening up of the vessels. That's speeded up. And then as they go back onto air, the blood vessels come down again. And this gives you another sort of pizza map from which you can find out both how big is that reaction of the blood vessels and how quickly do they react. So it's two different things, but they're both telling you about how well the blood vessels are working or not. And we know from a number of studies now that this ability of the blood vessels to open up falls with increasing age, sadly. It's one of those things, and a number of other things like blood pressure. But importantly, it leads to having worse white matter lesions a year later. It's worse if you've got more of these white matter hyperintensities, and also very interestingly, it's worse if you've got more of these little spaces, these little linear things, which actually on brain imaging, it's these spaces around the blood vessels which you get when the blood vessels are less healthy. And actually you can see them on MRI, and they indicate that the brain blood vessel health is not so good. And I guess, again, if that's what some of your blood vessels are looking like, it's not really surprising if they're not working very well. So, can we do something about this? So having thought about this for a long time and being aware that part of the problem is that the blood vessels are simply not working properly, they're not reacting properly, we wondered if there might be some drugs which might already be in existence and which might help to restore some of the blood vessel function. And we did identify a number of potential drugs, and if it's a drug that's already out there and used for another condition, then you already know what the safety profile is, so it's quite a good place to start if you think there might be some potential for benefit. So, again, cutting a long story short, we have now done a couple of trials. These are clinical trials. The first one is called LACI-1, Lacunar Intervention Trial 1, and it was just a little pilot, and we were looking to see if people with lacunar stroke and these blood vessel lesions would actually be able to take the drugs, because they don't normally get given these drugs. They cause headaches and things. And we found that, yes, they could, and the tablets seemed to be safe. So we went on and did a slightly bigger trial, and this one, the first was funded by the Alzheimer's Society, and the second one was funded by the British Heart Foundation. And we were interested to know if people could they take it for a year, because it's likely that you'd have to take this long term. And would we be able to get enough people into a trial to actually demonstrate whether or not the tablets worked? And basically, slightly surprisingly, in this second trial, we saw hints that these tablets together probably help reduce cognitive decline, and they reduce recurrent stroke. And they had a number of other good effects, and on the basis of that, and here we are in Southampton, the home of the National Institutes of Health Research, we are now about to launch a phase 3 trial of the same two drugs in the UK, and this will be the first phase 3 trial for vascular cognitive impairment, vascular dementia, actually anywhere in the world. So that one little observation, if anybody had told me when I saw that little funny blood vessel some years ago that this was going to end up as a phase 3 trial in vascular cognitive impairment, I don't think I would have believed it. But here we go. That's the power of observation, and it's the power of actually not just ignoring things. So where are we going? So first of all, basically this is not possible unless you have a really, really good team of people who are interested in the subject, but from an engineering, physics, chemistry, biology, and medical point of view. All of these machines, whether they're ultrasound or MRI or whatever, they're basically using waves. And when you're using one of these machines, it's a bit like trying to tune a really fine musical instrument to get the best possible notes out of it. It's exactly like that. And in the end, you know, when you get these amazing images, it's really quite like a sort of fusion of music, art, and biology. At least that's increasingly how I have come to think of it. And sometimes when I've been doing really complicated ultrasound on somebody's blood vessels in their neck, and you're trying to hear the signal, it is literally just like trying to tune into a very specific note. Where we were before, and we're going into the future, we have AI everywhere. There will be AI in your scanners in the hospital down the road. Some of it's good, some of it's hyped, some of it's not so good. I think we need to be cautious. We have much more sensitive scanners coming in, and increasingly mobile scanners, so that if you have a stroke, the scanner will come to you in the ambulance. And these amazing images that are starting to come out from things like photon counting, CT, you know, these amazing detailed micro almost images of the wiring in the brain and the tiny blood vessels. So really it's very bright in the future, but we do need to be aware that we need more efficient scanners. They use an enormous amount of energy. And although the government is very keen to introduce many more scanners into hospitals, I don't know that, you know, really we need to just think about how these are going to be used. So I just wanted to leave you with a few final thoughts. I think are apposite. Any sufficiently advanced technology is indistinguishable from magic. I think that's probably true. Never trust anything if you can't see where it keeps its brain, notably AI. With great power comes great responsibility. And the worst one, get a scan and then I'll see the patient. No. If I ever hear another neurologist say that, it's just absolutely not. This is where, with these amazing technologies, we actually need the best clinical skills ever. Otherwise, we just end up with a misuse. We scan people for the wrong reasons. We find things we didn't want to see. We don't know what to do with it. And we're just wasting vast amounts of public money. And the one thing that I really don't understand is at the end of the day, why would you discard the knowledge and experience from somebody who's been and had to get top grade exam results at school. They've spent 5 years at least at medical school. They've done all of their postgraduate training, including doing all their membership exams, and they've probably spent many years as a consultant. And you're less prepared to believe what they think might be going on than something that you get from spending a few minutes in a scanner. I really think we need a better balance of, these are machines, and if you put your clothes in the washing machine and they don't come out clean, you're probably going to get another washing machine. So, you know, these are tools like any other tools, and we need to get them in proportion. So, thank you very much for your time, and I'd just like to thank the funders and the researchers.
Thank you very, very much. Thank you very much. I think you'll agree with me that this was both inspiring and and informative. I'm sure that there are questions both in the room and online, and our colleague Professor Wardlaw's monitoring the online questions. So anybody from the room first, and we have our ambassadors. Professor O'Connor, over there. Yeah.
Don't need that. Thanks very much. I enjoyed that. I wanted you to sort of give an explanation about the two things and how coupled they are. You implied that the small muscle lesions are associated with break in connectivity based on white matter tracks, and then there was a functional reduction associated with the lesions. So I wonder which way round it goes. Do you think it's been driven from the parenchyma to the blood vessels, or the blood vessels are causing the interruption?
Very good question. So, traditionally one would think that something goes wrong with the blood vessels and that causes direct damage to the tissue roundabout, like the white matter fibers connections. And that is true to an extent, but it turns out that it's a little more complicated than that, because in addition to any direct damage that the blood vessels, when they're damaged, can do, it also turns out that when the blood vessels are a bit irritated, they can interfere with the way in which the white matter tracks are put together. So they can interfere with the adequacy of the wrapping. So each neuron fiber has a little fatty cover which insulates it, makes the signals go faster. If you don't have so much of that fatty cover, then your signals won't go so fast. And that may be partly why we're seeing people speeding up and slowing down depending on whether these lesions are getting bigger or smaller. So yes, there's a simple connection, but actually there's a bit more of a complexity underneath it. I don't think we've got any good evidence yet that the problem starts actually in the white matter and then damages the tissue, the vessels. I think mostly it seems to be predominantly going the other way, but keep an open mind.
Number which said 45% of dementia was associated.
Yeah.
It's a bloody high number.
Yeah, it is.
And you would then ask the question if the things that are associated with neuronal dysfunction are actually mediating the effect through blood vessel effects. So does the neuronal pathology drive an unresponsiveness to the blood vessels?
No. So far, most of the evidence seems to say it's the other way around. Okay. Even in Alzheimer's, the reason that there's that range, 20 to 40, 20% is vascular dementia, where vascular is the single main cause, and the main cause of that is this small vessel problem. This is also common to occur in people who also have Alzheimer's pathology. So you get what's called a mixed dementia. And if you add those together, then it's up to 45-40% in total.
Would you like to sit down for the next questions? I think there was one here. We have the magic student.
My thanks too for a wonderful lecture, absolutely fascinating. Could you talk a little bit about the use of imaging for brain injury? And I'm not thinking quite so much about traumatic brain injury, but the sort of progressive brain injury that sports people suffer from, maybe footballers who are heading the ball and rugby players who are crashing into scrums who might be suffering progressive brain damage, and whether there is a role for this sort of technology.
Another very good question. So classically, it has been thought that when the ball hits your head or you hit someone else in a scrum or something, that one thing that can happen if you hit someone quite hard is that you get a sort of shearing of the white matter tracts. And that's one possibility, and if that happens repeatedly, and even if it happens on a minor level, if it happens repeatedly, it might build up and so on. But it wouldn't explain things like the link with specifically with Alzheimer's disease, which we're seeing in a number of footballers now. And I've increasingly wondered whether, when you get a bang on the head like that, yes, of course it affects your neurons, but it also transiently affects your blood vessels. They kind of got sort of almost like stunned. And I didn't have time to go into this, but I mean, this is your particular area of interest. The blood vessels and the spaces round about them have a big role in getting rid of all the waste from the brain. And if you have a bang on the head, it may upset that waste clearance system. And that, in the long term, may also mean that you're getting a build-up of stuff which you should have been clearing out, but because that system's being damaged. This is pure hypothesis.
You say it much better than me.
But so there's a number of explanations of how that point of contact could lead to subsequent, gradually and progressive accumulating brain damage, which expresses itself in the form of impaired memory and other cognitive functions. But there's a lot of research going on about that at the moment.
From not just from our research in Southampton, but international evidence, any impact and any insult on the brain, whether it's traumatic or whether it's toxins, air pollution, smoking, will also result in subtle changes of the extracellular matrix, which is essentially the cement in which all these cells live. And if that matrix is affected, then everything going through it is going to be more sluggish and will start building up as amyloid or tau. There's a question there.
Hello. Excellent, fascinating. I mean, truly inspiring. I was wondering, you mentioned about the hyperintensities, and from a basic science or fundamental point of view, I mean, you sort of attributed it to probably vessel leakage, probably damage. What exactly is it in terms of, because intensity for me, I mean, I'm an imager too, means that there is a signal which indicates that there is accumulation of water or proton density,
Exactly.
sort of, So what is it in it that actually is happening there? Why do those cells or that area of the tissue becomes retentive to water?
Well, it is water. You're exactly right. Anything water. I mean, magnetic resonance imaging is basically imaging water. And the more water you have, depending on whichever sequence you're using, it will look brighter or darker, whatever, just depends. I think that's one of the reasons why these apparent areas can get better, because water can get cleared when, for example, if it was permanent myelin damage, actual structural punching holes in the tracks, then that would be much harder to repair. So this coming and going may be a reflection of accumulating water that shouldn't be there in the interstitial extracellular space that you mentioned, either because of the leakage letting a bit more out than it should do. And that's one, I think, reasonably okay, some evidence to support suggestion. The other is that these clearance mechanisms aren't working as well as they should do. And so, water that should clear is just not clearing as well as it should do. So I think it's probably, like everything, there's always more than one explanation. But anyway, and once the damage is more long-standing and permanent, yes, you do get destruction of the actual nerve fibers and the sort of myelin wrapping and so on. And then I suspect that that's much more difficult, if at all possible, to recover from. So, but there's probably a transient phase, at least in the early stages, when the early development is happening, that you get this fluid increase. And then, fluid in the wrong place in itself is toxic, so it will damage the nerve cells, the white matter, etc. And if it's there for too long, it will cause more permanent damage. So it's kind of why I think, if we could just do something more about this more effectively, then we might actually be able to stop that damage building up so quickly in the first place.
And earlier. We'll go to the questions online. Brigitte.
Yeah, there's a question from John Chandler online relating to your to your trial. I'm asking about the purpose of nitric oxide in the treatment.
So nitric oxide itself is one of those really fundamental molecules without which there is no life. In the case of the blood vessels, it plays a particularly important role because it helps to control things like the relaxation, the opening up when you need more blood to a particular bit of the brain, or overall. So it's really important for sort of micromanaging that, second to second, minute to minute, increase, decrease where it's needed in the brain. And classically, in people who have this blood vessel damage, they have much lower levels of nitric oxide. So simply by giving a drug like isosorbide mononitrate, which has been used literally for decades in cardiovascular disease for the treatment of angina, lo and behold, it seems, if these results are correct, to also have benefits in the brain, manifesting as less recurrent strokes, better cognitive outcomes. And interestingly, in that very first little pilot study that we did measure cerebrovascular reactivity to carbon dioxide, and we saw improvements in the ability of the blood vessels to dilate when challenged with CO2, and that was after even just about 8 weeks of treatment. So that just seems so simple, it's ridiculous that something's missing, so you give it, and it helps. And of course, the history of clinical trials is littered with early promising results that then are not replicated in larger definitive studies. So
we are hopeful here, though, because our
but
Japanese...
But there are other drugs like that which help to preserve nitric or work on a different bit of that pathway, which are already being used for other conditions and could be very worthwhile testing. We just picked those two, so other drugs are out there.
Angela.
It's fascinating, thank you very much. So out of all of those kind of advanced MRI technologies, some of which we're doing here, trying to do, which of those do you think could translate to new either diagnostic or prognostic tools that could then help either diagnose the patients that will best benefit from the drugs or manage those patients going forward?
So there are, I think, some useful structural images. So if there was a way of getting a reliable estimate of brain volume, just really simple thing, how big is that brain, and by measuring the intracranial volume, how much has that brain shrunk from where it was originally? Because the thing about the brain is the MRI is an archaeological tool. Once you get to adulthood, your skull is fixed in size, and so it acts as a proxy for how big was your brain when you were age 20. So if you have a brain now and a brain then, you can estimate the degree of shrinkage, just that, and then an ability to repeatedly measure if people come back for more scans. Similarly, a reliable method for estimating the volume of those white matter hyperintensities. Those are both really... In terms of functional measures, we've actually now used that test for this CO2 test for challenging the blood vessels and seeing how well they react in 2 multi-center trials. So we used it in a trial with 5 different centers, some in Germany, some in the Netherlands, and 2 centers in the UK. And that was the primary outcome. And we showed that you could, one blood pressure reducing tablet was more effective in terms of improving blood vessel reactivity than the others. So it's already at that level, but it's quite a... you can do simpler versions of it. You can get somebody to hold their breath, but that's for my PhD. Yeah, no, absolutely. The only reason we don't do that is because for the sort of population and the degree of repeatability that we want, it's a bit more varied. Some people are good at holding their breath. Other people are not so good. Yeah. So, but that's a simple version of the same thing. So.
Before we go to Jake, and we have another one from online, because Brigitte's list is getting longer and longer.
Yes, getting longer. So there are 2 related questions from Nicholas Weir. May I ask what you think actually causes a small, deep infarct?
Is it a thrombotic occlusion in some cases and vessel leakage in others? And then he follows up, after all the wake-up trial showed benefit of TPA in some small deep infarcts, but it does not seem that clot is the whole story.
So hello, Nick. If it's the Nick Weir, I think it is.
Yeah.
Hello. Yes. So I suspect that what may be happening in those small strokes that get noticed by people is that you've got this blood vessel wall problem that builds up, and then a sort of final thing that happens on this very kind of abnormal vessel wall is that that's the kind of thing where you can get a secondary clot forming. So it's quite possible that a little final clot forms, and that's what triggers the final sort of symptom complex. And so when you then give a drug which dissolves clots, there's some evidence in some people with that type of stroke that it might work, but there's actually quite a lot of other evidence that it isn't very effective. Perhaps because I suspect what also happens is that you actually get areas where you get those vessel wall abnormalities, and some of that apparent abnormality around about the vessel is actually water. You know, it's not necessarily ischemic as such. And at the moment we don't have that level of detail, but you know, it would actually be quite an important thing to do. I mean, this is a funny type of stroke. All sorts of other things happen that suggest that it's not just a little clot in a vessel. So I would just temporize that slightly.
Should we go to Jay and then Tracy? Yeah.
Thanks. Thank you for such a fantastic talk. I was really inspired by how you described going from a small feasibility study to imminently going to start a phase 3 study looking at those 2 drugs in vascular cognitive impairments. So I wondered if you could comment, looking back on the challenges you faced going through that process, but also looking forward to what you hope might come off the phase 3 trial, and when these drugs, if they show what you think they will show, will be available in clinical practice.
Okay, another good question. So I would say that at every single step of the way, there have been multiple barriers. Even just doing the original observational research that led to those trials, trying to persuade a funder in the mid-2000s that it was worth trying to see if the blood-brain barrier was abnormal in this condition took 3 applications before somebody funded it. To get the LACI 1 was 1 grant. LACI 2 required an initial submission, a rejection, and then a resubmission. And interestingly, the other trial that got funded at that first submission was negative. So, you know, pick your winners. In terms of then getting funding, so first of all, the LACI 2 trial, which is the 363 patient phase 2, which we're now gone to phase 3, it was hit by COVID. I mean, every single possible thing that you could possibly imagine could go wrong went wrong. The data monitoring committee tried to stop it because they said, what's the point of doing this? Literally. And I think they were just in a bad mood. And we said, but you haven't got a good reason for stopping it. There's no evidence of, you know, they weren't seeing any safety concerns. Anyway. So then when we applied to the NIHR, because that's the big trial funder, none of the other charity or other funders, you know, have, etc. It took, you have to put in an outline, then you put in a full application. They didn't quite like that one, but we could put in another application if we really wanted. So, you know, with like multiple hoops. So, and the one good thing out of all of this is that because, I mean, these are generic drugs. They are literally as cheap as chips. This would be like aspirin for vascular dementia. I mean, it's that level of cheapness and wide availability if it works. And there's an organisation now called NHS England Medicines Repurposing Programme. And they were very interested, and they helped us talk to the Medicines and Healthcare Regulatory Agency. I don't know if anybody's here.
No.
And I have to say, so we had to put in yet another application to the MHRA to get some advanced scientific advice, so that if, in the end, excuse me, LACI 3 confirms these results, that will facilitate a license extension to include leukemia, stroke, vascular cognitive impairment. Because otherwise, you get a positive result and then nothing changes because the license doesn't change. So we've had the advice, and we've incorporated that into the design of LACI3, and it's currently with ethics and all the other regulatory approvals. I have to say that the MHRA were far smarter and sharper than any of the other parts of the review process, because one thing they said was, we noticed that it looks like these two drugs might help each other, and if you get that apparent benefit in LACI3, somebody might want to make a single pill that contains both drugs, and then that would mean instead of having to take 2 extra pills, you only take 1 pill. And I thought, oh my God, you know. So anyway, it's going to take, we hope to start in January. The first patients won't be recruited till probably March. We've got a lot of interest from sites around the UK. However, there's aspiration and then there's reality, and I don't know how many will actually take part. We've also got interest from other countries. It's going to last for just over 4 years, so we've allowed for longer term follow-up, so 18 months instead of a year of follow-up, because I'm worried that we're missing something with the second drug. It maybe needs a bit longer. So we should have results literally in 5 years from now. That's everything is 5 years, But unless it gets stopped early or something else happens, or we have another COVID, or I just give up.
No.
Honestly, how hard does this have to be? Anyway,
this is very important for all of us at all our stages of
I mean,
career,
every single step has been at least 2 grant applications, every single paper. So when we first tried to publish that stuff about these hyperintensities getting smaller, we got all these reviewers' comments about, oh, you just can't work your scanner properly. You've just adjusted the settings. And, it's like, no, this is the same scanner, exactly the same sequence. We have a phenomenal quality assurance program because we don't want the thing to drift and start producing funny results. But this is the stuff you get. And eventually somebody said, oh, yeah, maybe. And then another paper came out with a similar finding. Anyway.
Tracy,
Thanks,
you're probably
Rox.
one of the last, if not.
Yeah, I think it's great to see progress in small vessel disease. I think really, really promising because it's horrible pathology. Is there a surrogate vascular bed that you can use that's easier to access, such as the back of the eye, that might give you an indication either of someone's vulnerability or someone's responsiveness?
Yep, good question. So yes, there are, with the eye, you can take a range of different images of different levels of smallness of blood vessels, and there are associations between changes in the arterioles and venules at the back of the eye and the structural changes in the brain. Perhaps more importantly, we have some pilot early stage data indicating that the changes in the blood vessels actually, over time, if you track people over a period of time and you relate changes in those blood vessels to changes in the brain in the context of a treatment, for example, that you can see changes in the blood vessels that mirror a return to a more healthy state, alongside evidence of improvement in things like blood vessel reactivity in the brain. So it's early days, but there may well be a sort of high street equivalent where, for example, you could show a flashing light because that stimulates, very much like it stimulates the brain, it stimulates the eye, and literally just measure that responsiveness. Because I think often it's, the structural side of things, the static side is fine, it's important, it's great, but it's actually how well are they working that's probably a bit more direct. So yes, that's, I think that's coming, and this group's interested in that.
Thank you so much. I could listen to this forever, of course, but I'm acutely aware of time. If there are no other questions, I would like to thank you again.
Oh, thank you for having me.
Thank you, everybody. I think, I don't know if we have a cup of tea before we go or not. I'm inviting everybody to a cup of tea. Thank you. Thank you again. And thank you to you for being here, and to the audience online. And thank you, Brigitte, for managing that beautifully.